Recording is not started.
Just now I started here. Just now, the previous lecture I did not record.
Okay.
Okay. So now I had discussed that lossy compression. We have many lossy compression algorithms, JPEG and TEC2 and so on. So now here I'm sure everybody must have seen this kind of thing, that when the quality level reduces, you can very clearly see the artifacts, right? So here it is just 5% the original size, but this is probably unacceptable. Maybe this is okay. This doesn't have so much errors, but this one is really unacceptable. Similarly, here this is no compression. This is heavily lossy compression. So this is definitely unacceptable. But that means some medium degree of compression may be acceptable. So always we have to see how much approximation is tolerable, how much is not tolerable. We had discussed this. Now this atomic operation last time I just mentioned. So avoiding atomic operation, that time, yes, last time I had told that we can skip atomic operation. So right now I just wanted to introduce what is atomic operation. Okay. So now this is a code in OpenMP. Okay. OpenMP is one multi-threading parallel programming language. It's not a full language, but it's just it is like an extension on the top of C or C++. So here, for example, we launch n threads. Here, for example, we have 10 threads. So what it means is this piece of code will be executed by 10 threads in parallel. Okay. You can actually just take this code and run it on your laptop, even if your laptop may not have 10 cores, but it will run. Now, but one thing is we want to count the number of threads. Suppose this is a very, very simplistic code. Here, I wanted to show you the use of atomic. So what we do in atomic is that we are counting how many distinct number of threads are there. So we want this piece of code to be executed by only one thread at a time. That means only one thread will enter this code at a time. When one thread has exited, then next thread will come, then next thread will come, next thread will come, and so on. So when we run this, because we have 10 threads, so obviously we'll get total number of threads as 10. Okay, but suppose we comment it out. Suppose we comment, we don't have this atomic construct, right? We allow any number of threads to simultaneously execute it. Then can anybody tell me how much will be the value of count which will be printed? If you know about parallel programming, then you can answer. Otherwise, it's difficult.
So 1.
Okay, who said 1?
So Priyansh.
Okay. Actually, every time you run, it will be different number. It could be 10, it could be 2, 3, 4, 5, 6, anything. That's the whole point, because this will be called race condition. Because see when multiple threads are running in parallel, we have no control over it at what speed they are running. So it is just like that. For example, suppose you have a joint bank account. Okay. Now sometimes if those bank people do not enforce this atomic condition, what will happen? Suppose you and your friend, suppose both of you have this joint account. Then you go, suppose there is only 1,000 rupees left in this account. Okay. Now you go and you withdraw 1,000 rupees, and your friend also goes in some other branch and he also withdraws 1,000 rupees. Then although your account had only 1,000 rupees, but you have withdrawn 2,000 because both myself and my friend, we were withdrawing the money in parallel. Okay. So that means the banks did, after I withdraw, the bank did not update that now balance has become 0. Now they cannot allow any more withdrawal. But mistakenly they allowed, because they did not allow this operations to happen in atomic manner. That means while I am withdrawing, nobody else can withdraw. Okay, this is the basic. This is the very intuitive condition, right? And especially nowadays, you can access your account by UPI or online or maybe physically. So many ways you can access. So there are very high chances that you can simultaneously withdraw. That's why always you can allow only one withdrawal at a time. Otherwise, it will lead to error. So that's what will happen here. So now you can see that only one operation, although there are 10 threads running, but only one thread can go inside this command at a time. So now that will call serialization. That means although 10 threads are running, but only one thread can go at a time. So that will lead to thread serialization. So that's what we had said is that atomic operations cause conflicts and they call thread serialization. So in approximate computing, if we know that, okay, some errors are okay, then we can avoid those atomic operations. But if some errors cannot be tolerated, then we cannot skip those atomic operations. We have to do those operations atomically. Otherwise, errors will happen, like this bank over withdrawal in the bank. It will be really nice, right? You just open a joint account and let all your friends or whoever is joint account holder, let them simultaneously withdraw. You get more money than what you deposited. So that will now of course, now as I said, banking is a financial is a domain where approximate computing cannot be used because it is high stakes. But we are talking about many applications where atomic where approximation cannot where approximation can be applied. That's why you can skip atomic operation because errors will be introduced. So actually, if you want, I can even demonstrate it. Let me demonstrate this. Okay, we have this now. Let me share all of my screen. So I hope you can see my screen, right? Can you see my screen?
Yes, sir. Yes.
Okay, so this putty is there. Now I will show you that this here I have actually just first I will run this command with dash f open. So we have to use this to make it run by f open. So g plus plus dash f open empty atomic. The binary which I create is so now whenever you run it will only give 10. But now let us change this. Now we'll run it. Sometime 4, sometime 5. Okay, any number you can get. Because why this? Because all these threads are running in parallel and they are overwriting, right? One thread works and other thread just overwrites that same value. So that's why a lot of race conditions are happening. So this is the reason you can't do this without atomic. Okay, let us go forward. Thresholding, I think I had discussed, and this part we had discussed. For this, I have given, I think, a question in the homework, so that will make it more clear. Some student had asked a question, so okay, I think that's here itself. Okay, I think it's here itself. Yeah. So suppose we take 1 lakh images to classify. We have 2 options to choose from. Suppose we can either use KNN or CNN. And these are just names. We could use some other classifier. Now, KNN can correctly predict 60% images, and CNN can predict 90% images correctly, which includes the 60% images that are correctly predicted by KNN. For every image, KNN and CNN take 3 millijoule and 10 millijoule energy respectively. Now, first option is if you use CNN for all the images, how much energy we consume? Answer is 1000 joules, right? Because we have 1 lakh images and CNN takes 10 millijoule. Okay, so if you multiply it, you will get 1000 joules. If we first, as a second option, let us first use KNN, and only those images which are not correctly predicted by KNN, we'll try to use CNN on them. Now, how much energy we consume? So first of all, we'll apply 3 millijoule energy on all the 1 lakh images. Then only 40,000 are not correctly predicted by KNN. We will apply CNN on them. So now you can see that instead of applying CNN on all the 1 lakh images, we are applying only on 40,000 images. So now, how much energy we consume? Now, how much energy we consume? 300 plus 400. So total of 700 joules. So now you can see that originally we were spending 1000 joules. Now we are spending 700 joules. So now energy is reduced and accuracy is not affected. Right? Because 60% images we predict correctly using KNN and remaining 35% images we predict using CNN. So overall accuracy is same. It is just that our overall energy has been reduced by using the scalable effort design. That means let us try to use a simpler classifier first so that we don't have to spend a lot of energy on most of the images. Only on the difficult to classify images, we are using a complex classifier. So is it clear to everyone? Okay, so let's go forward. Now this part we had discussed. We discussed till this point. Okay. Now let us discuss new points. So now we'll decide. So till now we are mostly talking about approximate algorithms or software. Now we'll discuss approximate hardware or inexact. This is also called inexact hardware. So for example, in adders, suppose we ignore the carry, right? You have a full order, but you ignore the carry. So your result will be wrong. But because you have ignored the carry, you can do your computations faster. Okay, now I will give some more examples. Suppose we have multipliers or cosine transform. Here is first example. So my point is, most of the hardware you can design inexactly, right? Instead of designing all of them exactly, you can design them inexactly. So here is an example of sigmoid function. So sigmoid function is this red line. Okay, so that means sigmoid function has this saturating nature. That means after a certain point of time, that means after when the x exceeds a certain value, then the output value y that becomes constant, or that reaches a some value. Okay. Now to compute the sigmoid function exactly is very costly because it requires exponentiation. Then you have to add, then you have to divide. So it is very costly to compute. So better is to realize it through a lookup table. Okay. So that's why, for example, like log, we always use lookup table for log. Generally, we don't all the time compute the log. We just use a lookup table. Now how large that lookup table is, that is in our hands. So here you can see the green one. So green is a very coarse approximation of sigmoid. Okay. So here, how many levels are there? 1, 2, 3, 4. That means our lookup table will have only 4 levels. So that is very lightweight lookup table. But if we are not happy with this kind of coarse approximation, we can be more refined. We can be more precise. So you can see the blue one. So blue one has more levels. It is also more accurate. Okay. So now you can see we can have different degrees of inexactness depending on. So here the green one is approximate by small LUT and the blue one is approximate by large LUT. Okay. So depending on how much preciseness your application requires, you can use different LUT tables. Okay, similarly, we can achieve 10H function by piecewise approximation. So as you know, 10H function, again, computing it exactly is very costly. So here we have used this simplification that when x is above 16 or below -16, we just use the value 1. And between -16 to 16, we can use a piecewise linear approximation of activation function. So because it is just a polynomial, it is easy to compute. Okay, compared to the exact 10H, which will require exponentiation and so on. So that means from the hardware implementation perspective, this will not have much difference in the accuracy, but it will be very fast for computation. Okay, now let us take an example of an approximate adder. So these are the equations for exactly computing the sum and out. So if you the carry out. So I'm sure you know full adder has a input carry and A and B. So full adder takes 3 inputs. One is A, second is the B, that means the 2 numbers and the input carry. So our output carry is found out by this and our sum is found out by this. Okay. So these are the exact expressions for carry out and sum. Now let us use approximate adders. Here what we do, we first compute the cout exactly. Okay, so cout we compute exactly, and then sum we don't exactly compute, we just take the inverse of cout as the sum. So here you can see that because we have 3 inputs, so we have total of 8 possible combinations, out of which now in this accurate output, all the couts and sum, they are all correct. But in this approximate computation that we did, right here, for 2 out of 8 cases, this case and this case, our sum is wrong. The cout is correct in all the 8 cases, but our sum is wrong in 2 out of 8 cases. Right? So now actually this cout can be computed just by using a majority circuit, and majority circuit is easy to compute. Okay, and for sum, instead of having this very large expression, we have just computed it as an inverse of majority logic. So now sum is very, very easy to compute, very, very quick to compute, although it will have errors. So 2 out of 8 cases, it will have an error. So if that kind of error is acceptable to you, then you can use this approximate adder. And another thing is that, for example, what you can do in the MSB part. So as you know, the larger adders are designed by adding smaller using smaller adders. For example, if you have to do q plus m plus k bits for whatever numbers of q, m, and k, you will generally design them. Okay, a q bit separate adder, m bit separate adder, k bit separate adder. Now the LSB, that means the lower significant bits, they are not very important. So for adding the lower significant bits, LSBs, we can use inexact adders, and for MSB, we can use exact adder. Right? In this way, the impact of approximation will be reduced, because on MSB we cannot afford to introduce a lot of errors that will have a huge impact. But on the LSBs, we can use inexact adder. Okay, is it clear? Anyone has any question at this point? Okay, let us go on. So this was adder. Now let us see multiplier. So here, there are many multiplier designs possible which are inexact. I have just taken one example. So here is an example of one inexact multiplier. So let us take an example of 2-bit into 2-bit multiplication. That means we have 2 bits A1, A0 and 2 bits here B0, B1. Okay, so because we have 4 combinations of A and 4 combinations of B, total number of combinations here are 16. Okay, total 16 combinations are possible. Okay, now we just introduce one error. That means out of these 16 combinations, we allow one of them to become wrong. What is that? So here you can see this is 1, 1, which means 3. Right? So this is 3, and this is also 3. Right? This 1, 1 is 3. Everybody knows that. Now 3 into 3 is what? 9. Okay, but instead of 3 into 3 being 9, I allow it to be 7. This is the small error we have introduced. That means instead of 9, let us just make it 7. All other multiplications are fully correct. For example, this is 3, this is 2. So 3 into 2 is 6. So this is 6. So this is correct. This is actually 2, and this is 2. So 2 into 2 is 4. So this is 4. This is also correct. Just this number is wrong. This 1, 1, 1. Instead of 9, I have made it 7. And that is also not very large error. Changing 9 to 7 is not a very large error. But so what is the benefit here? The benefit here is that now for representing 9, I would need 4 bits. Okay, but for representing 7, I need only 3 bits. So what has happened is all the 16 combinations I can for the output for all the 16 combinations can be represented just by using 3 bits. I don't need 4 bits. So this leads to significant simplification of the circuit. So here you can see this is the accurate multiplier where I need to generate four output bits. Okay. And here, this is the inexact multiplier where I need to generate only three output bits. And here, how much is the largest gate count? 1, 2, 3. That means to generate out 2 will be the slowest, which will, because here this signal has to propagate through three gates, whereas here just 2 gates. Right? This signal is generated just by 1 gate, and this these 2 signals they just take 2 gates. So instead of 3 gates here, now we just have maximum 2 gates. So I can get it faster. Plus I have only three outputs. Okay. So you can see just one small approximation has significantly simplified my circuit, multiplier circuit. And now again, the same, just as we did cascaded adder, similarly we can have this chain of larger multipliers. We can build multipliers of higher bit width by using inaccurate 2 into 2 block to produce partial products, and then shift it as we do, like in multiplication. When we do multiplication, then we shift. When we do multiplication, we shift. So we add the shifted versions of the partial products. That's all. And again, for multiplying this least significant, I can use inexact part. For multiplying this most significant part, I can use exact multiplier. That is in my control. Okay. Now here is another problem where we can use approximate computing. So suppose we have some binary number. We use 8 bits to represent any binary. Suppose we use 8 bits to represent a binary number, even if it is smaller than this. So now we examine the bits from one end to another and count total number of bit transitions. That means how many times we have transitioned from 0 to 1 or 1 to 0. For example, suppose this is my number 64. Okay, so whose binary representation is this? Now, how many bit transition it has? 2, right? From 0 to 1 here, and then 1 to 0 here. Then there are no more further bit transitions. Only 2 bit transitions are there. Okay. So now this problem is important to reduce data movement energy in off-chip buses, because when we transmit, suppose we transmit this data serially. That means one after another, these bits are transitioning. So actually, in this off-chip buses, energy is consumed only when the bit changes from 0 to 1. As long as the previous bit is same as this bit, there is no energy consumed. That's why we just want to reduce the number of bit transitions. Okay, so our goal here is to somehow reduce the number of bit transitions. So first of all, in this slide, I have just introduced what is bit transition. Now we will use some technique to reduce the number of bit transitions. Now consider an approximate computing technique where we replace original number, suppose P, with a nearby number K, such that the number of bit transitions in K is less than that in P. Example, suppose instead of transmitting 64, can I transmit 63? It has a bit representation of this, which leads to only 1 bit transition. So that means instead of transmitting 64, if I transmit 63, now my bit transitions are reduced. So my energy in the off-chip bus will be reduced, although some error is introduced. Okay. Now let us ask this question. So this is just an example. Now here is the question to be solved. Suppose P equals to 34. That means my actual number is 34. It has this binary representation. Actually, this is Fi. Find a number K such that it is within error of 2, and K leads to least number of bit transitions. So here is so this is my original number 34. Now I am allowed to have either plus 1, minus 1, plus 2, minus 2. That means I can send either 32, 33, 34, of course, 35, 36. So whichever of these numbers has the least number of transitions, I can send that. Okay. So I have written their binary representation here. And now you can easily count the number of transitions. For example, here there are 2 transitions. Here there are 3 transitions. Here there are 4 transitions. Here there are 3, 4. Now anybody can tell me which number I should transmit. Anubha? Just a minute. Anubha?
So 32.
Yeah, 32. Okay. So this is the answer. So if I, instead of transmitting 34, if I transmit 32, I will have lower energy in the off-chip bus. Okay, although some error is introduced, but obviously we can tolerate that error. Okay, now here is another example, approximation to save storage space. So actually, full idea of this you will understand when I discuss the floating point numbers, but at least we can easily, I'm sure a little bit insights everybody will have. Suppose we have 2 numbers. Now we store them in single precision format. So single precision requires 32 bits to store each number. Our goal is to store these values with lower number of bits. Okay. We are not allowed to increase the bit value, but we are allowed to slightly decrease them. Okay. So after approximation, what should be the value so that the number of bits which are required to represent them can be less than 32. So if you attended the tutorial, the first tutorial, you will remember that the number 5.7 actually becomes 4 if you throw away the least significant bits. So this is a similar idea you have to apply here. So I have given you a hint. A value that is power of 2 or sum of power of 2 values can be stored with less than 32 bits. Okay. a value which is either power of 2 or sum of power of 2 can be stored with less than 32 bits. With this hint, can anybody tell me, Isaac, Matthew? Isaac, Matthew. Shrikant? So the point is, instead of 3.52, if you can represent it with a number which is sum of power of 2, you can store it with less than 32 bits. So now can you tell me? Gaurav Ranjan? Think of a number which is sum of power of 2 and is smaller than 3.52. So for 2.05, I'm sure it is extremely easy. Right? Gaurav Ranjan. Find a number which is sum of power of 2 or power of 2, which is just smaller than 2.05. Okay, anybody?
So 2 to the power 1.
Yes, yeah. For 2.05, you can just store it as 2. What about 3.52?
So 2 to the power 0 plus 2 to the power 1.
So that is 3, right? This is 3.
Sir, plus 2 to the power minus 1 also.
Yes.
Yes.
You're right. Right, you're right. Yeah, you are from electronics. I can say that. So here, this is the number 3.5. 2. So 2 to the power 0 plus 2 to the power. So this is 2 to the power 1. This is 2 to the power 0, and this is 2 to the power minus 1. Okay. So now actually you can go back and see this number 3.5 versus 3.52. Which one of them will require less number of bits? That means even if you were to skip the least significant bits, you can represent this number exactly. Okay. So now further, let us see. Reducing branch divergence in SIMD. So see, till now we have not discussed SIMD, but here anyway, we are just discussing some approximate computing techniques. So what happens in SIMD architecture or GPU architecture is that we have suppose a warp with certain number of threads. Okay, suppose here we have 8 threads. Now, whenever we have if condition or switch condition, then for some of the threads, they will go through this path. They will go through this path, A path. Some of them will go through B path. Some of them will go through C path. So due to the SIMD architecture, this A, B, C cannot be executed in parallel. We have to first execute A, then we have to then we have to execute B, then we have to execute C. So that means when A is executing, although these threads do not execute A, but they will remain idle. Similarly, B part, only one thread is active, remaining 7 threads are inactive. So that is a huge waste of resources. So as you can see that percentage input data, which causes divergence, then as it increases, execution time increases a lot. Okay, that means GPUs are not good whenever there is divergence. Divergence just means that whenever we have a lot of if-else conditions, such that some threads execute if part, other threads execute else part. So how do we deal with it? Now, can anybody think what could be a way? How can we deal with it? We are allowed to do approximation. Okay. Now, can anybody think how we can use approximate computing idea to reduce the overhead of branch divergence? Bhanu Prashant or Suman, just think out of your mind, what could you approximate? You are allowed to do aggressive approximation. Mohit or Narendra? Okay, let me discuss. See, the whole idea is what we'll do branch herding. So what is the branch herding? So find outcome of majority of the threads and force all threads to follow that path. For example, here, see only one thread executes the part B. So let us either not execute it, that's one possibility, or let us force this thread also to follow this path A. Of course, we are introducing an error. That's all approximate computing is all about. So here is an example. So for example, in this case, now B part is the followed by least number of threads. So we can ask this thread also to follow either this thread or either this path or this path. Let us take an example. Suppose we have this array which has original value of this. Now here we have 16 threads. Some of them will follow this path. Some of them will follow this path. Okay. So you find out how many threads are following if part, how many threads are following else part. So we find out that most of the threads are following this if part. So if we use branch heading, then we'll force all the threads to follow the true part. Okay, that means all the 16 threads will force them to follow this path. Now some error will be introduced because their new value will be different than what it should be. But the point is execution time is reduced. So that is what approximate computing is here. So here is another example. So a GPU work has 16 threads. We have an array 16 whose values are this. Now suppose we execute this code. Now each iteration of this for loop is executed by one thread of a single bar. Now if you use branch heading strategy, we have to write expression after completion of the above code. So the answer is condition is true for most of the threads. So due to in some cases condition could be false for most of the threads. Then all the threads will follow the else part. So due to branch heading, it will be true for all the threads. So after the code, all the threads will have this array I plus equals to I. So the original value was this. Now the new value will be 122 plus I into 5. Okay.
Sir,
now this, yes, please.
This one.
Yes.
Sir, in the previous one, do we eliminate the else statement then?
Effectively, it is eliminated. Yes. No thread will execute it.
Okay.
So, like you will agree, right? Some errors are introduced, but that's fine. We assume we can tolerate it. Okay. So, and any other question, please?
Excuse me, sir.
Yes, please.
Sir, if you can just go to the previous slide, sir, where you were showing that A path and the C path, sir.
Yeah.
Sir, in this, when we are giving everything to path A, sir, like in
All
this
the
case,
threads, all the threads to path A, yes.
Yes, yes, sir. And B is totally vacant, sir.
Yeah, no, that means no thread will execute B part. Yes.
Then B will be utilized for some other process. That is what we are trying to gain with this, sir.
No, B will not be used by, nobody will execute B. So see, right now we are having 3 steps to execute this code. Then after our doing branch heading, suppose we just discard B, then we'll have only 2 steps. First A, then C.
Sequential.
Yeah, it will be sequential.
Sir.
So the whole point is we are executing sequentially, so we want to reduce some of the steps.
Okay, one step is reduced, sir. Right. Sir.
Yeah, one step is reduced.
Thank you, sir.
Okay. Now this is in non-volatile memory. Some of you may not know non-volatile memory. That's fine. So suppose we have any memory, right? Now to do the read or write exactly, we need certain amount of energy. Okay. If you do not do the write exactly, then that write will fail or read will fail. For example, whenever we are writing any memory, if our read current is very low, then there are errors in the read. Or if we do not apply the sensing duration for a sufficient amount of time, or if we apply too much read, then the bit gets flipped. For example, suppose you take a very old manuscript. Unless you are very, very careful, even in trying to read it, you will spoil it. You will either write something or you will just tear away the pages. So that is the idea of read disturbance. Similarly, in the write also, if your write duration is not sufficient or write current is not sufficient, then whatever value you want to write, that will not be written. Okay, so you can ignore this figure if this figure is looking difficult for you. But at least you get the idea, right? That means whenever we are writing something or reading something, we need a minimum amount of read current or write current or minimum duration of read or write current. So what we can do, we can use these knobs to control the quality. Okay, that means suppose we are writing LSB part. In LSB, it is okay to introduce errors. So we will, while writing the LSB, we will not apply full read current. We will not apply full write current. So some errors will be introduced. Okay, whereas when we are writing the MSB, we will write it exactly. We will make sure that the read current is sufficient, write current is sufficient. Okay, so what we will save? We will save energy, because once in a while the LSB may be written incorrectly, but that is fine for us because we are writing them with very less energy. So for example, here you can see as we increase the read energy, the read and error probability is very low. So what we can do, we can work here. Suppose in this range, we apply very less read energy. So instead of supplying 400, I will just supply read energy of 350. So some error may be introduced, but if I can tolerate that error, then I'll be able to operate my circuit with lower read energy. Similarly, here write energy, if I want 0 error, then I should have supplied maybe 32 picojoule. But if I supply suppose only 10 picojoule, I will have a lot of errors, but as long as I can tolerate that error, I am able to save write energy. Right? So that's the idea of approximate computing here. Okay. Now, here is similar idea. Suppose in PCM. PCM is another non-volatile memory that's called phase change memory. So one of the property of PCM is that the write operation is very, very costly. Okay, that means you see usually everybody would expect that reading something or writing something from a memory should take same amount of energy. But in PCM, write operation is very, very costly. So what we do, here is a proposed technique. If existing data are almost same as new data, we cancel the write operation. Just take the existing data as the new data. Okay. So see, the idea is, see, read operation is very cheap. So what we do, first of all, we read the old data, read PCM. Before, that means even for writing something, we first of all read the previous value. So that means some read energy is getting spent. But as I already said, read is much, much cheaper than write. So first of all, we read the old data. Now we have read the old data. Now we find out the new data. We compare it. If it is more than threshold, then we do the write. If it is less than threshold, we don't do the write. We just cancel the write operation. So here is an example. Suppose we have an 8-bit PCM. The old data was 60 and new data that we want to write is 48. Okay. Now suppose if our threshold is 24, then you can subtract 60 minus 48 or whatever, and then anyway you have to take the absolute value. So this 12 is less than 60. This is less than 24. Right. So that's why we can skip this write operation. Just take the, although we wanted to write 48, but we don't have to have 48. 60 is fine with us. So some error is introduced, but the biggest point is we have avoided the whole write operation. We have avoided the write operation on all the 8 bits. So we are saving significant amount of energy. Okay. Now here is a Taylor series approximation. So by definition, this is an approximation, right? So I'm sure at least you would have heard of what is a Taylor series. So in Taylor series, we write a polynomial, okay, to get the value of something, and depending on how many, how many expressions you take, how many number of terms you take, you will get a more and more accurate answer. So for example, if I want to find out the this cubic root of 8.1, this is the number I get. Okay, so this is the number which I get by just taking 3 terms, and this is the exact answer. So this is the exact answer. Okay, and this is the answer I get just by taking 3 terms. So the point is, just by taking 3 terms, I get an answer which is accurate up to 6 places of decimal. If I want to have more precision, I can take more and more terms. Instead of 3 terms, I can take 30 terms. But the point is it improving the accuracy? Maybe it will improve accuracy by maybe 4 or 5 more digits after decimal. But I will anyway throw away that. My computer anyway cannot work with that much accuracy. So why compute so many terms? Just stop at 3 terms. That's the idea of Taylor series approximation. Okay, so by definition, actually Taylor series uses the idea of approximation that more number of, more your budget is, you can go on increasing more terms, you will get more accuracy. But the question is, do you really need that much accuracy? Okay. Now another is in image processing. This is very interesting. We can ignore unimportant parts of the image and still get good accuracy. So suppose this is our original image. Okay. Suppose this is our original image. Now, there is a software called GradCam. If you don't know it, that's fine, doesn't matter. So what we do in GradCam, here it produces a heat map of the pixels which are important to classify this cat. Okay, so this red part shows which pixels are most important to identify that this is a cat. Similarly, this part here shows which pixels are most important for recognizing dog. So I'm sure this is very, very intuitive, very, very illustrative. It's easy to understand. Now, as you can see, suppose forget the cat. Let us just focus on dog. So for recognizing this dog, all I need is this area, right? For classifying that this image is a dog, we don't need to worry about these pixels, right? All these pixels which I'm doing as red, they are unimportant. Okay, so I can approximate them. I can store them inexactly. But if I do any approximation in these pixels, I may not be able to recognize this as a dog. That will be too much error. Okay, so that error is intolerable, but the error in remaining pixels, which are not very important for this CNN to work, those pixels can be approximated. So let us take an example. So here, what I'm doing is we are cropping certain images. So this is our original image. So as you can see, the spider is in just a center. Usually what happens, the object of interest is in the center part. So usually the corner pixels are not very important. So here, this is the result on the original image. So this is the actually there is some new line should also come. I should show the new line. So here, the confidence that this image is a black and gold garden spider is this one. So more the confidence, the more we are showing the result. Okay. So our confidence that this is a black and gold garden spider is 0.71. It is just a garden spider is 0.2. And barn spider, wolf spider, black widow, and so on. These are the very less confident. Now, this is the result if I center crop the image. That means I remove the corner image. So in fact, not only we don't have to process all that image, right? We don't have to process any of this area. We don't have to do any computation on that area. Not only that has happened, but our confidence has also increased. We are now less distracted by the corner images or corner pixels. We are now focused only on the image, and now we are even more confident. So not only the computations have reduced, but our confidence has also improved. Usually our accuracy may also improve. This is another example. This is the overall macaw image. Macaw is a type of parrot. Here now we crop certain parts. In fact, we have maybe, but you can say by mistake or whatever, we have even cropped some part of the macaw itself. But still, our results have not become wrong. In fact, our confidence that this is a macaw has improved. Okay. Similarly, here is a maze. So previously we were this much accurate. Now again, we still have the same surety. So that is good, right? We are now, you can see there's so many distracting things we have reduced. We have removed so many distracting things. Now we just need to, processing all that would have taken so much computation. We are avoiding that computation. Finally, in this vehicle, we have cropped the corner parts, and now previously we were 0.986 sure. Now we are 0.998 sure. We are really, really sure that this is a recreation vehicle. So in this way, by ignoring the unimportant parts of the image, we have improved the accuracy. Okay. So another is, here is an example. How, any questions till this point?
Sir?
Yes.
Sir, how we are getting the increased accuracy, sir?
Yeah, so that is good. So see here, at least in these cases, we have purposefully not cropped the useful pixels. We have just cropped unimportant pixels or useless, distracting pixels. Actually, it's not accuracy. It is actually confidence. Confidence is different from accuracy. The point is, confidence just shows that how confident I am in my predicting this thing. How confident I am in saying that this is really a recreation vehicle. And accuracy is defined by, if I predict, suppose 1 lakh images, how many of those images are correctly predicted? Forget confidence. Whichever is the highest confidence, that is our prediction. Now, if I predict 1 lakh images, how many images are correctly predicted? That is my accuracy. So accuracy here, we have not said anything. At least in these 4 images, our prediction has not changed. So our accuracy is 100%. But confidence has improved because we have removed the distracting pixels. Okay. Okay. So now this is actually I should have included this figure in a early, but this is so here what we are doing object detection. So in this image we are trying to detect where are the vehicles. So actually there are 3 vehicles here, 1, 2, 3. So this is the mask. We are doing instance segmentation. Okay. So these masks are generated, and from this actually it's called intermediate output, but it's a mask. It's an instance segmentation mask. So from this mask we can correctly find out that there are 3 vehicles. Now suppose some error happens because something becomes faulty. Either circuit is hardware is faulty or software is faulty or whatever. Now suppose from this our mask changes to this. Okay, suppose our mask changes to this. Then it is an unusable output. Why? Because we are detecting even those things which are not vehicle as vehicle. So this is a big mistake. But as long as our mask changes, so here you can see compared to the first image, now my mask has changed. Okay, my mask has changed, but it is just that little bit shape has become different. So actually just the bounding box size has increased. So this red thing is called bounding box. So I'm not detecting any other object as vehicle. It is just that instead of a very tight bounding box, now my bounding box is slightly loose. That's fine. It is still usable. It's not perfect, but it is usable. So that the point is, as long as your errors are between this to this, it is acceptable, it is tolerable. But if your error becomes from this to this, it is intolerable. Okay, so that means small errors I can allow. Those errors which just change from this to this, I can allow them. Maybe they can allow us to save energy. But if the errors become too much such that from this I go to this, then that is not acceptable. Okay, so certain faults I can allow so that because I can still work correctly, but certain faults I cannot allow because they will cause too much error. Okay, next thing is, so is it clear, the previous example, or do you have any question? Okay, now next is deduplication. So deduplication means we are avoiding the duplicates. Suppose we have this original data. I want to find out which are the distinct or unique numbers which are coming. So here I just have 4 unique numbers, A, B, C, D. We are getting many repetitions of that. That's a separate thing. But the distinct numbers are just 4, A, B, C, D. Okay, so this process is called deduplication. Now here we are doing duplication exactly. Deduplication we are doing exactly. But I can also do it inexactly. How? Like this. Suppose we have these numbers. If I were to do exact deduplication, I will find out that this is duplicate of this, this is duplicate of this, this is a duplicate of this. So I can remove those duplicates, and then I just get this. Okay. Now I can do approximate deduplication where I ignore the LSB while comparing the numbers. I ignore the LSB. So once I ignore the LSB, what happens? This and this also become similar. Right? These two also become similar. So then now after deduplication, my size of table has further reduced. Instead of 4 entries, now it has only 3 entries. I've written as X means don't care. Anyway, you could either replace it by 0 or 1, doesn't matter because we are not worrying about the LSB. Okay, so this is called approximate deduplication. So is it clear to everyone what is approximate deduplication? Okay, so then finally, this is the last example for today. So here we are doing frame skipping in a video. I will illustrate it. So what happens, like, as you know, a video is what? A video is just a, many frames put together, and they are played at very fast speed so that our eye cannot distinguish it. Okay, it is just that our eye cannot distinguish it because we have so many frames. So I have an input MP4 file. Its duration is around 19 seconds. Okay, and its speed is almost 30 FPS. Okay. So this is, I will show you the input MP4 file. Okay, which has a duration of 19 seconds. Now, its speed is almost 30 FPS. That means 30 frames per second. Now I ran some script. So what that script is, this script skips every second frame. That means out of the total 544 frames that I had, I skipped almost half of the frames, and the remaining frames I wrote it in a vout.mp4 file. That means now I have generated another MP4 files which just has half the number of frames. So especially, as you know, right, there are many slow motion videos. So I don't have to see all the frames. Even if I were to say half the frame, I will get most of the essence of it. Okay. So now I will show you both the frames. Now here you can see instead of almost 19 minutes of 19 seconds of video, now I just have 9 seconds of video. I may not have, suppose 19 seconds. All I have is 9 seconds. So with this 9 seconds, I can, instead of seeing V in, I can see V out, but I can still capture the essence. Okay. In this way, I'm doing approximate computing. It may happen if the video is very fast motion, I will skip many useful details. But many videos are usually slow motion, so there is not much change. So I still don't lose a lot of information. So let us see this. So this is the original video. It's little bit fast motion. It's not so slow motion. Okay, some motion is there. Okay, so now let me show you the. Oh, sorry. This was the V out. I should have first played this. This is the input video. Okay, as you can see, it is a somewhat slow motion. It is not so much changes there. It is relatively slow motion. Okay. Now let me show you the output video. So this is the output video. Now it is much faster, right, compared to that, because only half of the frames are there compared to the original frame, compared to the original video. So that's what we did. We took a 19-second video. We skipped half of the frames. Now we just have half of the video, which has only half of the frames. But I'm still getting the essence of the video, what it is. All the important frames I still have. Some of the frames which are probably duplicate of the previous frame, they are gone.